12.4 Complex fractions. A complex fraction is a rational expression that contains fractions in either its numerator, denominator, or both. Basically, it's a fraction within a fraction, and no one likes that. So here's an example of a complex fraction. You'll see x over 2 plus 4 in the numerator, and in the denominator you'll see another fraction, 2 over x minus 1. So we have the main fraction, which is the numerator of x over 2 plus 4, and then you'll have internal fractions. For instance, in the numerator it's just that x over 2 has an internal fraction. Our goal is to diminish the number of fractions we're dealing with and to have only one single numerator and a single denominator. Now that could be a binomial or a trinomial in the numerator and denominator, but no fractions. And why we would want to do that is because it would allow you to evaluate your expressions more quickly, and it's easier to determine the domain. There's a few strategies. One is to multiply the main numerator and denominator by something that eliminates all of the internal denominators, and you'll use the least common denominator to do this. So in order to do that, you can find the least common denominator of all internal fractions and multiply the main fraction by 1 in the form of a lowest common denominator over a lowest common denominator, and simplify it, stating any domain restrictions. So this will be example 1 that I do for you. I'll do both of these, and then you'll have an opportunity to try it yourself. So in this first one, I have 8 in my numerator and 4 over 9 in my denominator. And I'm going to give you my method for doing this. So I will rewrite the first fraction bar as a division symbol, and I will write the second fraction out. And in this one, I can simply turn the division symbol into a multiplication symbol by taking the reciprocal of the second number. So this will become 8 times 9 over 4. Now it's a lot easier to simplify. If you need to see it as 8 over 1, you can, and then we'll just multiply the numerators and the denominators together, and we'll get 72 over 4, and we can divide both the numerator and denominator by 2 to simplify, and that is 36 over 2. Can divide it again, and we'll get 18. Alright, and most folks could agree that 18 is a lot nicer than 8 over 9 over 4. This next one has 2 fractions in the denominator, so the first thing that we'll do with this one is we'll add the 2 fractions in the denominator together. In order to do that, we'll need common denominators in the denominator, and we will have 8 over 4/9 plus, oh goodness, what is 16 times 3? Well, I know the denominator's 9. That's 8. Is it 48? Now I can add the 2 fractions in the denominator together, and we will get 52 over 9. And I can do that thing that I was doing before, where I can turn that fraction symbol into a division symbol, and that will allow me to take the reciprocal of the second fraction. I think we have enough room for that. We'll have 72 over 52, which can be simplified to be 36 over 26, which can be simplified to be 18 over 13. And we can stop there. Now, with both of these, we didn't have to do a domain restriction because there were no x's. And so what I want you to try yourself will be these next two. 3 is a lot like the number 1 that I had done for you, and it might help you to see 7 as 7 over 1 for that one. And number 4 is similar to the second one I had done. You'll need to combine the numerator together before you begin. I'm going to do one more example, and this one will have a domain restriction. Okay, so for this one I am going to write out the question, and I'm also going to take this opportunity in my writing out the question to make that middle division symbol, that middle division line, a division symbol. And then I'm going to change it to a multiplication symbol by taking the reciprocal of the second fraction and leaving the first fraction alone. Now be careful when you multiply. It might be helpful to put parentheses around these two terms so that when you multiply you remember to distribute. So this first numerator will be 9x squared plus x. The x gets multiplied to both terms, and the denominator will be x squared minus 8x. And we can see, well, I can see at least, that there's an x in all of the terms, so we can probably factor an x out of everything. So I'm going to take that work on up here and rewrite what I have, and I'm going to factor an x out. Okay, now I can cancel those x's, and some of you might have seen that we could have canceled those x's earlier over here in our first step. Good for you, I didn't see it. And we now have 9x plus 1 over x minus 8. And that's as simple as we can go. Now with this one, we'll need to state our domain restrictions. And you can't just look at the final answer because we would just think that x couldn't equal, again, think to yourself, what x creates a 0 in the denominator? That's 8. So we know, at least that one, x cannot equal 8, but x can't equal other things. You gotta look at every domain that there was, and there were a lot of domains. So I'm gonna look at this top fraction. So there's an x value that creates a 0 in that top fraction, and the x is in the denominator, so 0 can't be an input either. And then we also have the denominator of the main fraction was x minus 8 over x, and that one couldn't equal 0. And that one takes a little bit more thinking. So this one, x minus 8 over x, couldn't equal 0. So I got to think about what could make it 0 and multiply both sides by x. Doesn't really matter because it multiplies by 0, so now I have 0 equals x minus 8. I got that plus 8, plus 8. So there's that other x value that couldn't work, which we had already seen from our previous work. So we got them both. So x couldn't equal 8 or 0. Make sure you check each denominator. That's an internal denominator, that's an internal denominator, and this whole sucker there is a denominator of the main fraction. So you got 3 places to check when you're thinking about your domain restrictions. And that will be it for us. I've got 2 independent questions for you to try and 1 problem for your groups to work on.